Hello. Now we'll see the charge distribution onto a concentric spherical shells. So we are having two concentric spherical shells. They are shells, basically they are hollow. The outer shell is having a radius B and the inner shell is having a radius A. And obviously the B is more than A. They are concentric, so their centers are common. Now to the outer shell we have provided the charge QB, positive QB charge, and the inner shell we have provided the charge plus QA. Now we want to see how this charge QA and QB will get distributed over to the inner and outer surfaces of these shells. Okay. So let's have some thickness actually. So this is your inner shell and this is your outer shell. So I've made some thickness because later on I'll be making a Gaussian surface within this shell. Okay. So now this QA charge, let's say out of this QA charge plus QA dash goes inside. So remaining will go outside, so that is QA minus QA dash, because the net charge should be same. And this out of this QB plus QB dash goes inside surface, and the remaining will go at the outside surface minus QB dash. And obviously we know that these charges will be distributed uniformly over to the surfaces because there is a spherical symmetry there. Okay, now we want to check the values of QA dash and QB dash. I'm calling these surfaces as 1, 2, 3 and 4. Okay, now I'll be drawing Gaussian surface. So this is my first Gaussian surface. So as you can see, my first Gaussian surface, I'm calling it G1, is completely inside the first spherical shell. It's completely inside. And this is going to be my second Gaussian surface, which is inside the outer shell. So I'm calling it G2. So now we'll apply the Gauss law for G1. So Gauss law for surface 1, which is G1. So if I apply it, it is E dot ds, and that is equals to Q in. So if you see the G1, inside this G1 Gaussian surface, this is the charge. That is QA dash upon epsilon naught. Okay. Now see, since my G1, this Gaussian surface is completely inside a metallic spherical shell. So for that, E at each and every point will be 0. So this Gaussian surface, if you see, at each and every point of this Gaussian surface, since each and every point of this Gaussian surface is inside the conductor. So at each and every point, electric field will be 0. So that makes this QA dash upon epsilon naught to be 0, and that makes this QA dash to be 0. So that makes the charge at the surface 1, which is this surface, 0. And the charge at the surface 2, which is this outside surface, QA, because QA dash is completely 0. Okay. Now we'll apply the Gauss law for G2, meaning second surface we'll go for. So if we go for the second surface and apply the Gauss law, which is E dot ds, and that is equals to Q in upon epsilon naught, Q in upon epsilon naught. Now let's count the charge, inside charge. So for the second surface, if you see, the charge is this QB dash. This is inside the second surface. Along with that, this is also the charge, and this is also the charge. And if you combine these two, the QA, it is QA, combining these two. So the net charge inside the second Gaussian surface becomes QA plus QB dash, and divided by obviously epsilon naught. Now since all points in the second Gaussian surface, they are inside the spherical shell, all points on G2 are inside a conductor, and that makes electric field 0 for all the points. For all the points. So that leads to E dot ds upon ds. That leads to 0, and that's the value of qa plus qb dash upon epsilon naught. And this value will lead to qb dash to be equals to minus of qa. So charge onto the second Gaussian surface, charge onto the second spherical shell inside, it becomes minus of q. That's a negative charge which is coming there. So that makes the charge onto the third surface, that is third surface, as minus of qa, and charge onto the fourth surface, which is qb minus qb dash. So qb minus of qb dash, which is minus of qa. That makes q4 to be qa plus qb. Okay. Now let's draw this one more time. So if I'm having two spherical surfaces, and if I provide inside surface, if I'm going to provide plus of qa charge, so inside there will be 0 charge. All the charge will go for here. Then whatever is the charge here, if it is positive, here will be the negative charge. If this is negative, obviously this will be positive, because if you see the formula, charge onto the b dash will be negative of qa. So it becomes qa, and if outside I'm providing qb, so 1 plus qa is coming from the inside, because you see that this spherical shell was neutral before you provided the charge. So if the minus of charge is getting generated onto one side of surface, obviously plus charge will go to the other side of surface, and other side of surface is already plus qb charged. So this will become this much. So that's how you distribute the charge. So if you are having this number of spherical shells, so from inside you will start. Completely inside there will be 0. Whatever charge you are providing, that will go for the outermost inside shell. Negative of that will come to the inside of the next shell. Then algebra you will follow, net charge should be same. Then the same thing will proceed. Okay. So that's how we distribute the charge in case of spherical shells, conducting spherical shell. Okay. Thank you.